You've heard it 1,000 times. In movies, in textbooks, from people who sound confident, they know the answer. Astronauts float because there's no gravity in space. Movies like Gravity and Interstellar show weightless astronauts drifting through space, and the visuals reinforce this idea that gravity just stops working up there. That explanation is completely wrong. And if you've ever wondered why that explanation doesn't quite add up, why the moon stays up there if gravity disappears, you're not alone. That confusion is the first sign you're thinking critically. But here's the problem with that explanation. If there's no gravity in space, why does the moon stay in orbit around Earth instead of flying off? And why does the space station need constant maintenance to keep it from falling? The International Space Station orbits at about 250 miles above Earth's surface. At that altitude, Earth's gravity is still 90% as strong as it is down here. Gravity never disappears. It's always pulling on everything. The moon, the space station, every satellite in orbit. The reality is far more interesting than the myth. Astronauts float because they're in continuous freefall. And here's what makes it wild. They're plummeting at 17,500 miles per hour. That's 23 times the speed of sound. They're not hovering. They're in a constant race with Earth, and Earth keeps curving away just fast enough to miss them. That perpetual descent creates the weightless effect you see in videos from the space station. If you're tired of hearing oversimplified explanations about space, subscribe. Every video here cuts through the myths and shows you how the universe actually works. Freefall happens when gravity is the only force acting on you. Nothing else. No air resistance, no thrust from engines, just gravity pulling you down. When you drop an apple, it immediately enters freefall. It accelerates toward the ground at a specific rate. This seems backwards, right? A bowling ball and a feather should fall at different speeds. The bowling ball is heavier. But in a vacuum, with nothing but gravity acting, something strange happens. They fall at exactly the same rate. Why? Here's the key insight that makes orbital mechanics work. In a vacuum, all objects fall at exactly the same rate, regardless of their mass. A hammer and a feather would hit the ground at the same instant if you dropped them in a vacuum. On Earth, air resistance makes the feather fall more slowly, but remove the air and they fall together. But here's the thing that trips people up. If a bowling ball and a feather fall at the same rate in a vacuum, why does a feather float down so slowly when you drop it on Earth? The answer isn't about gravity. It's about something else entirely. Apollo 15 astronaut David Scott stood on the moon's surface in 1971 and deliberately dropped a hammer and a falcon feather. Millions of people watched from Earth, waiting to see if Newton's prediction would hold true on another world. With no atmosphere to interfere, both objects hit the lunar dust at exactly the same moment. That wasn't just a proof of concept. It was humanity confirming our understanding of the universe itself. Observable proof captured on video. If this moment blew your mind, humanity testing physics on another world, drop a comment telling me what surprised you most about how gravity actually works. I read every comment, and I love hearing what clicks for you. You've actually experienced this principle before? Not in space, but right here on Earth. Not in space, not in a plane, somewhere much more ordinary. Remember that moment on a roller coaster when you crest the top of a hill and your stomach jumps into your throat? That split second where gravity seems to let go? Or driving over a steep hill and feeling your body lift slightly from the seat? That wasn't your imagination. That was the same physics that keeps astronauts floating 250 miles above Earth. Your body and the seat were falling at the same rate, creating that weightless sensation. Think about a drop tower ride at an amusement park like Tower of Terror at Disney parks, or Drop Tower at Six Flags. The moment the ride starts falling, you experience a brief period of weightlessness for about 2 to 3 seconds. If you released a phone from your hand at the exact start of the drop, it would hover right in front of you. Not because gravity stopped working on the phone, but because you and the phone are falling at the same acceleration. The phone appears to float relative to you. This is exactly what happens on the International Space Station. Except the freefall never stops. The station is in constant freefall, which creates the continuous floating effect. This principle is what creates the floating effect on the space station. The station itself, the astronauts inside, and every object aboard are all racing toward Earth together. Because everything falls at the same rate, objects appear to float relative to each other. Astronauts don't feel the pull of gravity because there's nothing pushing back against them. On Earth, the ground pushes up against your feet. That's what you feel as weight. Remove that opposing force and you feel weightless, even though gravity is still acting on you. Scientists use the term microgravity instead of zero gravity. That terminology is more accurate because it acknowledges that gravity is still present and still acting. The prefix micro means very small, referring to the tiny gravitational effects that remain. These effects come from the station's structure, air resistance at that altitude, and the slight variations in Earth's gravitational field. But the dominant sensation is weightlessness because everything is falling together. The freefall state isn't unique to spacecraft. Anytime an object is falling with only gravity acting on it, it's in freefall. A skydiver experiences freefall until air resistance builds up enough to slow them down. A ball thrown into the air enters freefall the moment it leaves your hand. The difference with orbit is that the freefall continues indefinitely instead of ending when you hit the ground. Understanding this distinction matters because it reveals what's actually happening in orbit. Astronauts aren't escaping gravity. They're not in some magical region where physical laws change. They're simply falling, just like anything else that gravity pulls on. The floating you see in space station videos is the visual result of everything falling together at the same rate in the same direction. But to understand why the space station doesn't crash, we need to understand how orbit actually works. And the best way to understand that is through Newton's thought experiment, a cannon on a mountain that explains everything. Newton was wrestling with something that had haunted astronomers for centuries. They could see the moon orbiting Earth. They could measure it, but the mechanism, the why, remained invisible. How does something stay in orbit without falling? It seemed to defy common sense. So Newton imagined a thought experiment so simple, so elegant, that it would finally answer the question that had puzzled the greatest minds of his time. He developed this in the 1600s, and at the time this concept was revolutionary because it explained why the moon doesn't crash into Earth. His answer was so counterintuitive that people thought he was crazy. Imagine placing a cannon at the top of an impossibly tall mountain, high enough that there's no air resistance. Fire a cannonball horizontally from that cannon. The cannonball immediately starts falling toward Earth in a curved arc. It travels some distance horizontally before hitting the ground. Now fire the cannon with more gunpowder. The cannonball travels farther before landing because it has more horizontal speed. The curve of its path gets longer. Now here's where it gets interesting. Keep increasing the speed. The cannonball travels farther and farther. But at some specific speed, the exact right speed, something remarkable happens. The curve of the cannonball's fall matches the curve of Earth's surface. The cannonball is still falling, but Earth's surface curves away at exactly the same rate the cannonball falls toward it. That's orbit. The cannonball keeps falling, but never hits the ground because the ground keeps curving away. So how fast does the space station actually have to move to keep falling around Earth without crashing? Take a guess. Is it faster than a commercial jet? Faster than a fighter jet? Faster than a bullet? The answer might surprise you. For the International Space Station at 250 miles altitude, that speed is 17,500 miles per hour. To put that in perspective, that's about 23 times the speed of sound. A fighter jet in Top Gun, Maverick breaks the sound barrier at around 760 miles per hour. The space station moves so fast it would cross the entire continental United States in roughly 10 minutes. Let that sink in. The station is moving so fast it would cross from New York to Los Angeles in the time it takes to watch a TV commercial break. The astronauts aboard are experiencing speeds that would be instantly fatal if they tried to move through Earth's atmosphere. They're moving so fast that they orbit Earth every 90 minutes, seeing 16 sunrises and sunsets every single day. And yet inside the station, they float peacefully, completely unaware of the speed because they're falling at the same rate as everything around them. Think about that for a second. Right now, as you're watching this video, there are people hurtling through space at 5 miles per second. They're in constant freefall, and they feel completely normal. They can drink coffee, write in notebooks, sleep in their sleeping bags, all while plummeting around Earth. That's the power of understanding freefall. The station moves sideways fast enough that its downward curve matches Earth's curve. It's in perpetual descent but misses the planet continuously. This is why astronauts float. They're not hovering in place. They're plummeting around Earth at 5 miles per second. The station is in freefall, they're in freefall, and every object inside is locked in the same perpetual descent. Because they all fall at the same rate in the same direction, they appear motionless relative to each other. The floating effect is just this endless race toward the ground. But here's what's wild. The exact same physics that keeps the space station in orbit also keeps the moon orbiting Earth. The moon is falling around us, just like the station is falling around Earth. The only difference is distance and speed. It's in free fall around Earth. Gravity pulls the moon toward our planet every second. but the moon moves sideways fast enough to keep missing us. If the moon suddenly stopped moving sideways, it would crash into Earth. If it moved faster, it would fly away into space. The balance between descent and forward motion keeps it in orbit. The moon is racing toward Earth just like the space station, just at a much greater distance and a slower speed. So here's the paradox. If the moon is constantly falling toward Earth and the space station is constantly falling toward Earth, then gravity is still pulling on both of them. Yet people talk about escaping gravity as if it disappears in space. That's the real misconception. Gravity is always pulling. Always. Weightlessness isn't about the absence of gravity. It's about continuous freefall. Here's the paradox. The farther you go from Earth, the weaker gravity gets. So you'd think that eventually gravity would disappear, right? Wrong. Gravity never reaches zero. A spacecraft traveling to Mars is still being pulled by Earth's gravity the entire journey. It never escapes. It just moves far enough away that Earth's pull becomes irrelevant compared to the Sun's pull. The farther you go from Earth, the weaker gravity gets, which means you need less sideways speed to maintain orbit. The moon orbits at roughly 2,300 miles per hour because it's much farther away than the space station. Satellites in higher orbits move slower than satellites in lower orbits, but they're all plummeting. They're all locked in continuous descent around Earth. So here's what you now know that most people don't. Weightlessness isn't about the absence of gravity. It's about continuous freefall. Astronauts float because they're racing around Earth at 17,500 miles per hour, locked in perpetual descent. Gravity is always there, always pulling, always creating the dance of celestial mechanics. This is the truth that movies get wrong. This is the misconception that keeps people confused about how space actually works. And now you understand it better than the people who made Gravity and Interstellar. The next time someone tells you there's no gravity in space, you'll know the real answer. The next time you see a movie showing weightless astronauts escaping gravity, you'll see through it. You'll understand the physics that the filmmakers missed. Want to go deeper? The next video breaks down what happens when satellites stop falling around Earth and start falling toward it, orbital decay, and why space junk becomes a problem. Watch it now. If you found this explanation clearer than what you learned before, subscribe. Every video here cuts through the myths and shows you how the universe actually works.